Hello, so we are Team 8, the automated EMC calibration device. My name is Akash Akkiangadi. I'm in charge of purchasing and the power systems. I'm also accompanied by Aaron Carter, who is our mechanical engineering lead, Logan Kirkland, who is our material science and mechanical lead, along with Dustin Givens, who is our power systems and motor communications expert, and Dilip Badveli, who is our software programmer.
So there were a couple of very interesting material design choices that we had to make during construction of our device. One of the most interesting materials that we used to construct our project is called Delrin. It's this white plastic you can see in the bottom of our project. It's got some very interesting material properties. It's very resistant to wear. It's got a very low coefficient of friction. So we used it in places of our project that are going to be sliding back and forth against each other. Unfortunately, it's difficult to machine given the materials that the machining tools that we have access to. So we chose to use wood to construct the majority of our project. We used kiln-dried wood so that it would interfere with the electromagnetic field as little as possible. We used that to construct the U channel in the X, in the Y, and the X direction. It's low cost, it's easy to machine, and it allowed us to get a proof of concept up and running. And then we're going to allow Schneider to take our plan, run with it, make it future-proof, and reconstruct it if they so choose with Delrin. We also chose to use fiberglass for our threaded rod. We were actually originally planning on using Delrin for that part. However, we found out upon talking to machining experts that it's difficult to machine a threaded rod of that length in a lathe. So we fell back to our secondary option. We chose to use fiberglass. Turns out it's actually a lot better. It's easy to machine, it comes prefabricated, and it's a lot lighter than Delrin as well.
So for the driving mechanism for our device, we use what's known as a lead screw system. So we actually have a U-shaped channel and then this T-block which sits in this U-shaped channel. We have a threaded rod threaded through this block, which is attached to this block thanks to this bearing which is tapped to match the threads of the rod. So as this rod rotates in place and this end bearing and this coupling to the motor, as the threads progress, it pushes this entire mechanism back and forth. And the same technology is used for the Y system, except this block was kept short enough to where we could tap it all the way through directly. And thanks to this U channel, the sides keep the block from rotating with this rod. So again, as this rotates, it moves the platform up and down.
So you can see here, this is a UI I developed using LabVIEW, and then I have a myRIO controller over here. This controller is programmed with embedded C, and they both need to communicate with each other. I use something called TCP communications for this. So if you look at the screen, I could choose different positions I want to move the sensor to. You can see I click this. You will see here the command list of the different positions I want to move to. I can execute it, which will send a message to the myRIO, which will tell it to move the sensor to this position. While this is happening, I had to prevent this from getting any numeral commands or multi-executing the commands until the myRIO successfully has moved the sensor to the right location. As well, I can remove these commands if there is a mistake and use this, which gives you a more specific direction to move into. For this example, I'll be showing it move to the right by 1.5 inches and moving up by 1.5 inches. You can see that it got into the list. When I execute it, you'll see that the sensor is moving.
One of the most important product requirements for us is ensuring that our system can function in a high-strength electromagnetic field. And for us, that meant designing it with non-conductive materials.
Our design consisted of 3 distinct subsystems, the first of which is a software interface with National Instruments LabVIEW software, which is the current software that Schneider Electric utilizes in their lab. Secondly, we had a NI LabVIEW myRIO controller that interfaces between the software and the motors that we chose. The third is the actual test stand. It utilizes stepper motors and the controller outputting signals from the software to move to 20 distinct points on the XY plane within 1/8 inch accuracy.
So some challenges for us on this project was one, ordering parts. So some of the parts that we needed were from overseas. Some of the arrival deadlines were months. So that would put us past some of our deadlines for the deliverables on this project. So we had to sort of interchange parts that we needed based on availability and the time that they could get here. So there was a lot of adapting as far as availability of parts. Some other challenges were, of course, the mechanical aspects of it. One was the mechanical design. Since we're all electrical engineers, using AutoCAD to create mechanical designs was sort of a curveball for us. But after a lot of online tutorials and trial and error, we were able to adapt and become proficient with the software. Also, as far as the physical machining of a device, all of the parts, except for the prefabricated rods, were made by us. As far as we bought the raw material, and then we cut, sawed, and drilled, sanded, and tapped all the pieces and then put them together. So for many of us, it was our first time using heavy-duty power tools. So again, it was adapting to new challenges and learning on the fly.